Hello, my name is Matt Georgie, and this is going to be my honors capstone presentation. The presentation is on emergent design failure and path dependency in ship design. And in this presentation, I'll be focusing on the design I made for my NA470 senior design class. So first, to introduce the topic. So when you're looking at designing a ship, you're looking at designing a very complex systems engineering problem. And what this means is that every single design decision that you make, and when you're just exploring how to solve the design problem of, hey, I need to get these 3,500 containers from LA to Singapore, when you're looking at designing that problem, how to do this efficiently, how to do this safely, you're looking at a very complex problem, meaning that there's a lot of interdependencies. So for example, we could see here that this geometry of this hole is going to affect how much weight you can put on the back, which is going to affect how many containers you can carry in total. And on top of this, you put these containers in the back, that's going to affect your trim. And depending on how high you stack the containers, it's going to affect the stability. And all of these need to be very closely understood and analyzed in creating the design, because you don't want to have you want to pass regulations. You want to make sure that the design is going to work, it's feasible, and that it's also going to be safe. So I will be exploring design theory um, in this capstone project, and the general goal is to do that through my NA470 ship design project. And what we talk about when we're looking at this is, we call it the wicked problem, because in reality, you don't know what the design space is going to look like until you design, until you get there. And as a result of this, design failures such as rework, design churn, and failure to integrate can come up, and they come up quite often. And I will discuss how these came up in my design project. So first, to the theory. So the two design failures that I'm going to study in this and present to you is design churn and failure to integrate. Design churn happens when you're creating more problems than you're solving, and you're exploring knowledge structures that you don't need to explore. So if you look here, this is the key to these graphs. And basically what's happening is, when you're going through the solution, you do end up on the right path, but it takes you a lot more time and a lot more effort. Because what's happening is that I solve one problem and it causes another problem. And I'm not decreasing the amount of problems as I go on, which is definitely not how you want to design. And so that is called design churn. Failure to integrate is a very dramatic design failure in which you are completely off the required path. So this green path is the required path. This is the path that you need to take, the design decisions you need to make for the ship to work, for you to solve your problem. Failure to integrate is when you have a piece of information that you just don't integrate it into your design. So you continue on your design without integrating this, and it leads to this situation where I'm over here, I'm exploring these knowledge structures when I need to be over here. So the goal was to identify what aspects of my design failed and determine why these issues occurred. Further than that, I wanted to figure out where the design path began, why this continued, and I wanted to identify which aspect of emergent design theory this was related to. Steps taken. So in order to do this, I learned about the advanced design theory from Professor Singer. One of the interesting things I learned being a naval arc student is that the naval arc professionals and professors and those who are doing research are very big in this field of emergent design failure and complex system engineering problem. And that's obviously because the ship is a very complex system, a very huge system, and there's a lot of interdependencies. So those who understand this do very good in this field for other aspects, which would be automotive design and designs of airplanes. So the second step was to examine the NA470 design, determine where the design failures existed, and evaluate what design decisions created the emergence and why they were made. So the design failures that I identified were a excessive amount of trim towards the stern, towards the stern, which means that the ship was going like this in an excessive amount. So it was trimming towards the stern, meaning that there was a lot of weight over here, and that was a design failure. And the other two that I'm going to be focusing on for this presentation is that the righting arm for the ship was low for intact stability, and the righting arm for damage stability actually completely failed. So you can see below here is a righting arm. I believe this is one for my intact stability, and this just tells you the moment that the ship is going to have when it's at a certain helo angle. Okay. So first thing I want to talk about is that the bulkheads were placed with no input. Uh, and what I needed to understand to place these bulkheads was actually the floodable length curve. And I didn't do this. And that was my failure to integrate. I didn't know where I wanted to put these bulkheads and where I could put these cargo holds to make sure that when the ship flooded, when one of these compartments flooded, they would to make sure that when one of these compartments flooded, it wouldn't pass the margin line. And the reason why that's important is because you want to know exactly where you can place your bulkheads. And I didn't include that information, which ended up giving me a lot of trouble with my damage stability because that's when a compartment is damaged. So the second point I want to point out with the ship is that the stern transformation resulted in a poorly designed hole. So when I was looking at this project with Professor Singer, we actually learned that we we well he showed us that the actual whole design of the ship was not really optimal for the number of containers that we wanted to place on the ship. So we learned that going through. So this was the failure. So because I didn't integrate what happened, or because I didn't integrate the floodable length, I ended up having a design churn between figuring out a configuration for these 3,500 containers. And as you can see, the containers in the middle are high up, and these cargo holds are not used or barely used. In this case, these two only have 2 rows. And what happened was is that I ended up causing another problem with my righting arm curve, and it ended up not being able to, or it ended up barely passing the United States Coast Guard criteria. So as I was kind of saying, the failure led to a design churn between these two configurations, and it's because I didn't integrate the floodable length curve. So just to describe the floodable length curve a little bit, floodable length curve is the this curve indicates given a certain displacement, it indicates much how much of the hole can flood for each point before getting over this margin line. These triangles are the actual area of the hole, and this is in a 2D representation. So in the 3D would be a triangular prism, but this is a 2D representation. So as long as the area that is flooded does not go past this floodable length curve, meaning that it's not going to flood the margin line when the bulkhead is damaged, then you're passing on floodable length. And the important thing to note about this is that this can be very helpful in determining where to place these bulkheads and how long to place them, because it's one of the constraints. So here's my floodable length curve. And this is something that I actually just failed to integrate into my design. And I didn't take the time to realize kind of what it meant. And I didn't take the time to see my bulkhead placements under this and do the same sort of idea here with the triangles. Um, and so had I done that, I would have avoided this design failure. So another thing I want to talk about is the hold lines. And this is a little bit off of the topic, but it is a design failure. And it's a design failure that I actually couldn't control because the whole form was just kind of given to me. But had I had foresight and more experience in naval arc, I would have noticed this problem and been able to address it within my design. So one of so basically this is showing the back and the front, and you can see that in the back these lines are very fair, which means that they're not taking up a lot of volume, and so that means that as a result you can't have as much weight there. So I wasn't considering this, and it was another design failure. Damage stability. So damage stability is the intact stability curve given a damaged water type bulkhead. And as I've kind of been saying this whole presentation, because I didn't integrate the floodable length, this ended up failing pretty dramatically. And you can see that this is a really bad uh, GZ curve. It's a very bad riding arm curve because you can see that the maximum riding arm is a very, very low 0.226 meters. You can also see that there's actually negative riding arm. There's negative riding arm in the beginning. So that means that if the ship is heeling at these smaller angles, it's actually going to going to have more force as it tries to correct. So it's going to have force against the correcting. And so positive stability right here indicates that when the ship is tilting like this, the positive stability riding arm moment says that it's going to go back up like that. And when you have negative stability, it's actually going to go the opposite way, and the ship is going to sink itself. And this is a much better description of that. We have upright stability, and you can kind of see what I'm talking about. The center, when the center of buoyancy is creating a positive moment on the center of gravity. These things we have upright stability, and when it's the opposite direction because the center of gravity is actually over the center of buoyancy, we have inverted stability, negative stability, and that means that the ship is going to sink itself and it's going to flip by itself. In this case, the ship is going to actually correct itself. And this is just a bigger graphic of the GZ curve, how these could have been avoided. Understanding that so firstly, most of this could have been avoided through foresight and just more wisdom in naval architecture. I think that this capstone gave me a lot of opportunity to learn what I was missing in naval architecture, and now that I kind of understand that, that would help a lot in future designs. And so the very basic idea is that I could have taken into account floodable length curve, and I could have I could have understood what it meant and how I should have taken into account, which I didn't. And then also I could have anticipated the change in damage stability more, because when I did my project, the intact stability worked out, but it was a little bit low. And I thought that I kind of misinterpreted how low it was going to be when I did damage stability. And that ended up making me pretty much fail in damage stability when considering the criteria and the regulatory bodies that we were trying to be under. Anyway, that's my presentation. A lot of this is much more in depthly described in my report. So please take a look at that if you have any questions. And